Hello, hello. Hi, everyone. Good afternoon. Okay. I think I should start now. Okay. So, first of all, may I remind all of you that in the chat box, I upload a PDF to all of you. Can you see that in the chat box? No. Oh, okay.
No,
Wait.
not yet.
Okay. Wait. Let me see. Then I upload again. Okay. Wait. Interesting. I upload already, but seems not pose it. Let me try again. Sorry. Okay. Yeah. Hello. Can you check again in the chat box whether you see a PDF?
Yes.
Okay. Thank you so much. Okay. Everyone, may I remind you one of today's major topic related to this article. Although this is an old article, but what I want to say is quite interesting and important for today's discussion. So please accept it and download it for your future reference. Okay, let's begin. And thank you very much for all of you, okay, for joining this last lecture for the second radio school for Romania and Hong Kong. And the last topic we would like to discuss to you is Introduction to 21 cm Cosmology. And I would like to show you the contents, okay? Here are some contents, but I would like to introduce one more topic. In my presentation, we say that we will talk about the updated status for SKA. And before we talk about 21 cm cosmology, may I say a few words to all of you about the what we so-called SKA. So anyway, in Google, okay, I forgot to type this link to all of you, but it is simple. I don't know why today the Zoom bar cannot be automatically embedded. Okay, may I increase the font size? Okay. Everyone, you can easily access the following website. Maybe I pause it here. Please do wait. Okay, I put here. Hope you don't mind. Okay, I think you see this website. Am I right? The name for this website, skao.int.
Yes.
Okay, thank you. Okay, if you click on it, this is a very interesting website about the updated status of the SKA. And may I say a few words about SKA to all of you? And SKA corresponding to square kilometer array observatory, or we simply call it SKA, square kilometer array. And this is a big project between several countries. May I see any partners or the foundation member? Yes, SKAO member. In this website, you can easily to find this pull-down menus, and you can see many details information. They just updated this website half years ago, roughly. And these are the foundation member. Is it foundation or anyway member? Okay, Australia, China, Italy, Netherlands, and blah blah blah. India, where it is. Okay, they have several members. However, the number of members should be increased from my point of view. And may I remind you, this is a mega project, and several years ago, they confirmed to be construct such project, so-called square kilometer array, in both Australia and South Africa. And they cut it into two parts for the low frequency and high frequency, or even middle frequency. When I visit Australia, I remember I focus on their low frequency array, but they also have middle frequency, and in South Africa, they also well developed in high frequency. Okay, go back to the introduction. For this simple, for this big project, not simple, sorry. And this is quite interesting because you can see that here are the representative and important member all over the world about this project. And they try to construct many array and antenna into both Australia and South Africa. Okay. And here are some simple video and construction. So have a look for very short period of time. All right. So if you want to know the details, you can go to this website, and they have many resources, such as the updated news and events, and when they will have some conference or discussion, and the details, and their partner, and even resources. So here we just show you some, but I won't go through very detailed. To be honest, I'm not a member of SKA, although I tried before, but failure, okay? And may I remind you, their headquarters is located in Europe, in UK, in Georgia Bank Observatory, near Manchester. However, the site, observational site, were located in Australia, West Australia, Murchison, so-called MWA, Murchison Whitefield Array Observatory. For South Africa, they located in another desert. Okay, anyway, they call it Meerkat. So the details you can find from this website, but why at the beginning, when we plan to talk about this radio school, introduce this project, because this is a mega project first, and they concern many fundamental and important projects, and in terms of cosmology, astrophysics, and etc. And this is a mega project united so many countries together and invest huge amount of money and work together, and not only work based on the observation. We also, for this project, they lead many engineers. So for young people, for our radio school, in case you like to work on it, they have different aspects, such as engineering portion, science portion, and etc. So it doesn't mean you say I'm studying engineering cannot be related to square kilometer arrays project. No. From my point of view, engineer may be in the first priority from their project, because many technical problems lead engineer for help to solve. For example, they will construct many array on both Australia and South Africa. And here, okay, as I said, this is a new updated website, and they construct so many telescopes in two different positions. Let me show you one that I familiar a little bit. Okay, so in Google, you just type the MWA radio astronomy. Yeah, you can easily to see one of the important founder, SKA founder site. Okay. Any media? Okay. And I show you a few pictures. So you can see here the telescope. Yeah. Here are the telescope. Okay, you will say, Sing, this is a telescope. Yes, this is not like the traditional one I show you, let's say from our small radio telescope in Hong Kong. You can see that this telescope, which is fixed on the ground floor, and we call it spider. We call it spider because it looks like a spider, and the height around 0.7 meter. And you see, they have so many antenna, which is not movable. However, here is a machine. You can imagine they connect all these 16 antenna. And for 4 times 4 antenna in total means 16, 16, 16. We call it one tower. Around 5 years ago, they updated up to here, how many tower? 512, if I remember correctly. Okay, 512 tower. So you can easily to calculate the total number of antenna they have, 16 times 512 tower. And they finished the second phase upgraded for this antenna. Then you may say, why they install so many antenna on the ground floor? Because they want to collect the large field of view radio signal in different position on the sky, or even in different Earth, different time scale for our universe. Okay, we will tell you more details later. So this is our telescope. May I remind all of you? Okay, although not moving, and they don't worry about the poor weather condition, because they put on a desert. Of course, most of the time very hot and good situation, fine weather. But the time I visit here, was not like this blue sky, was cloudy condition, not frequent like this. However, anyway, this is a good location, one of the good location in the world, I would say, for radio observatory. And the other, of course, right now in Chile, Atacama. And the third one, like what Dr. Hodgson last week mentioned, in Antarctica, okay? And so here, the most important thing to construct a mega project is related to some location. So you can imagine in Hong Kong, not a good location. I think Romania may have some good position and location. Think about it, whether you can install or not for teaching. Let's say, even for our Hong Kong case, I plan personally, I would like to buy several antennas to see whether I can form one tower for learning, for teaching. Because you will ask me, saying they don't have any moving parts, how come they can check the object on the sky? In fact, not necessary. This is the low frequency radio astronomy compared to high frequency. Their beam size means their coverage or their resolution, corresponding to very, very large beam size, may up to 70 degree. Okay, for our small radio telescope in Hong Kong, our beam size is 4 degree roughly, and here 70. So they look at the sky all the times. And why, you may say, then the reason is they need to look at different position, and they major focus in low frequency range. If I remember exactly, usually from 100 megahertz up to 300 megahertz, so very low frequency. For this case, what we so call the atmosphere, okay, there is an ionosphere in our atmosphere, and all the time will affect the signal that they receive, because low frequency radio astronomy now is quite important. You heard many radio astronomy discovery, but most of the time they focus on high frequency. For example, the one I mentioned in Atacama, and they work on very high frequency range. However, why they work in low frequency range? Because some important result probably may related to low frequency. But why not work on low frequency? For the case, let's say in Hong Kong, the low frequency radio astronomy, this band, let's say 100 mega or less than that, the pioneer use it for doing radio communication at the beginning. So you can imagine the pollution was very serious. However, why now have a little bit change in our Hong Kong case? For example, like the taxi in Hong Kong, most of the taxi driver, they will install a radio receiver to receive the order from location A to location B. However, right now they have changed. They may use mobile phone. They may use the mobile phone, so may have a better possibility to study it right now. So I plan to work with my team to see the low frequency radio astronomy, see whether we can study it in Hong Kong. Okay, don't say much. And here is one of the SKA founder. What does it mean? It means before we construct the SKA all over the world, we have to do some prototype or some testing, and they install in Western Australia before, and doing the calibration or the first phase of their work, they also have a fruitful publication. Why? Two major reasons. One is this is biggest add together, as I mentioned before, in total, how many tile, 512 or even 1024. You know, the collecting area roughly equal to a square kilometer. Okay, compare, for example, even like in China, the biggest single dish, which is lock steerable, so-called FAST, F-A-S-T, the diameter is 500. However, here is 1 square kilometer. Can you imagine? So their collecting area is bigger than that single dish in China. And of course, the larger the collecting area or the dish they have means the higher sensitivity they have. So once the SKA full function in Australia and South Africa, the sensitivity will higher than FAST. Okay, this is normal. And of course, next reason why they construct so huge mega project in the world, because they want to study some fundamental and important question related to cosmology or astrophysics. So give you some simple example why, let's say, America and European Space Agency, they launch what we so-called planned satellite or WMAP or COBE or even James Webb telescope right now to our outer space. The reason was they want to confirm some result that they observe outside our Earth means less pollution or distortion. They want to confirm the result, or they want to study more and more details about the result, and that's why they launch it. However, this is a good work, but too expensive. Our ground-based telescope, of course, has their advantage in some sense, because you know every time you launch to the space, you can easily to imagine that in case they have some failure, not easy to fix. But for ground-based telescope, we can relatively easily to fix it, or even we replace it. But it doesn't mean space telescope not important, very important. Okay, so the most effective way is combine the space probe or space telescope and the ground-based telescope together to do observation at the same time. Okay. So I don't go through the details for this array because at least if we need to talk about that, or we need to add 2 extra lessons. And I'm not a suitable person. Okay, probably invite some committee member or the core member for SKA, such their chairman. Okay, Professor Phil Diamonds. I met him several times in China and other locations. Okay, now go back to what I want to say today. Please wait. Okay, apart from SKA, sorry, please wait. Yes. And today we also want to introduce what we so-called 21 cm cosmology. And may I remind all of you, 21 cm cosmology, the name, you should pay attention. And this is so-called an observational cosmology. Observational cosmology. You see, cosmology can sometimes distinguish in theoretical or observational. And both are important from my point of view, okay? Because observation can provide some evidence to convince the people who study cosmology, or one of the ultimate goal for observational cosmologies is to know and present to the public the history of our universe. Okay, this is a big problem. Okay, when you study cosmology, for example, how the universe formed, how did it evolve, and these are so-called big problems. Okay, originally maybe 2,000 years ago, most of the time they try to answer it based on philosophy. Okay, but right now, due to the equipment and technology become more advancing, so some observational result can be very precise related to cosmology. That's why they have a sub-branch from cosmology, so-called observational cosmology. So today, the target for so-called 21 cm cosmology is an observational cosmology. And I will introduce this briefly, okay, briefly. And so first of all, let me say a few words. And all these details, for example, here I would like to look at the overview, what we so-called EOR. And why so many short forms? Because when you study this field, let's say like the photo I show you in MWA, when I visit or join the radio school, they teach me, they use this EOR corresponding to what they observe and study. So they have used the spider telescope array and MWA and have answered several fundamental problems. And one of them is EOR. And this is related to an epoch in the history of universe, so-called epoch of reionization. We will tell you more about that. And this overview was written by one of my idols, the former department head from Harvard University Department of Astronomy, Professor A.V. Loop. And very lucky, I watched some of his uploaded video in YouTube about this part, and he introduced to the public many times about this 21 cm cosmology. Okay, I will go back to this slide. And now, let's say, okay, show you some simple picture first. Usually for the people who study visible universe or observable universe, they will use this diagram to represent something. So this is our concentric circle. You can imagine in the middle corresponding our universe today. And as I also introduced several times, when you meet some cosmology, you talk to them about the size of our universe or some specific location. You can also use redshift to talk to them. Of course, you can talk to them, say how the age of our universe, okay, the age of our universe. But at the same time, you can also use redshift to talk about that. And then you may say, most of the time we say that our universe has 13.8 billion years old or 13.7. I don't care at this moment, okay? And how come we can know about that? So you can imagine, even right now, you look at the screen, and the screen can display you the information, probably how many nanoseconds that you observe. I mean the screen that shows you log the same times that you understand everything on the screen. Or another example, maybe you go out, assume today have a good weather, you do sun bathing, and then you see the sun, you enjoy the sun, but you know the sun is not at the present moment. It belongs to around 8 minutes, 19 seconds before. So if you capture the result or take picture for some specific position, you got the photo and object, then this is so-called the look back image or look back time. So here we are here, and then you see first circle corresponding to the radius equal to z equal to 1, and another concentric circle z equal to 2. So if you look in this direction, means this is what we so-called look back time, and we look at the history of our universe. All right, and you see here we will have two layers, one corresponding to this shaded area, we call it reionization, and hydrogen recombination, and z equal to 1100 here. And if you keep move on, you can see this figure show you z equal to infinity, okay, means very, very large, very, very large. And here z equal to 1100 based on the theory they said. This is the result that what the scientists detected, so-called CMB layer. So this is our visible universe. So in this direction, redshift is turn, and this is the time starting from, let's say, Big Bang. Okay, and the, I cannot take all this. Okay, major challenge in astronomy, and this is a slide from Professor Yang, okay, from China. And you see, most of the time we write down a proposal to get funding. Nowadays, probably we can try to write down, we want to answer these 4 fundamental problems, like what we so-called end of a dark age and formation of first generation star, and dark matter, dark energy. And on the lower left corner, we will say the ecology in the universe. And the last one may be the origin of planetary system and life. So these are fundamental and big challenge in astronomy. And today we major focus on the top left-hand corner, end of the dark age and then formation of the first star. And this is also an illustrated diagram to illustrate the timeline or the brief history of our universe. And you say, as we mentioned, the age for the universe roughly after Big Bang expansion, 13.7 billion years. And here with some light, you can easily to count each difference corresponding to 1 billion. Okay, let's say here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Can you follow? Can you follow? One difference around 1 billion years. Okay, this diagram. And another interesting things from this illustrated diagram, you see after this what we so-call quantum fluctuation or Big Bang, they have an inflation, and here is very short period of time. May I remind all of you the inflation period? Maybe usually nowadays we will say 10 to the power minus 36 seconds up to 10 to the power minus 34 seconds. And our universe, let's say, expand 10 to the power 26, the order of magnitudes. Yeah. However, from this diagram, what we can look is that here with a period so-called dark age, and here after Big Bang 400,000 years, I mean the afterglow for the our universe expansion after Big Bang, then we detected, okay, on 1967 or even Kobe 1992 or WMAP and Penn satellite and etc. And what we so-called the CMB and isotropic and isotropy for our universe. However, on this side, you can also imagine this is our infant or baby universe. And similarly, on another side of this diagram, let's say here, the last circle, you can imagine this is what we can easily observe even for the amateur people at night. They use a good quality small optical telescope. They can easily to capture the galaxy or some star. So here is an illustrated diagram about that. From this diagram, we also load some information here for this inflation period. Although this is not detected anything at this moment, because what we can detect is only up to this layer, this CMB layer, after roughly 400,000 years after Big Bang. And before that, many people want to study it or even try to detect any signal, but right now not easy. Okay, and maybe the gravitational spectrum or detector, maybe they can detect. Okay, by the way, so this is some simple history and illustration. However, you may not satisfied by this picture. Why? Because, sorry, wait. What I want to show you, I lock this one. Okay, and what I want to say, yes, this one. This way. Okay, yeah. This is the materials that I upload on the chatbot and share to you, and this is come from Scientific American 2006 and number 11, okay, volume 11. And this gentleman, he wrote an interesting article, so I would like to share to you. If you are the beginner, I think this is a good article to all of you. So as an observational cosmologist, right now they publish a book about our universe. You can imagine this picture. I want to tell you, this is a photo album of an observational cosmology books. You can imagine, and you can see that most of the page in this photo album or this book, which is blank or dark. However, at the not front page, okay, in the first few pages, you can see on the lower left corner, we have a photo, what we so-called CMB, the baby universe. You can imagine this CMB result similar to the unborn babies unborn babies ultrasound photo, okay, and similar. So the unborn baby is still inside in the mother's body, okay, and at the same time, near the end of the box, you will see some galaxy or some galaxy cluster. I don't care, okay. So in between them, if you buy a book like this, are you satisfied? Are you satisfied? This is a book, okay, published by some observational cosmologies. Of course, you will not satisfy. So same as that, the observational cosmologies also not satisfied. So they try their best to tell you, or even they study more the detail. How come the baby universe start from this CMB result and change into the result that we can easily recognize at the last page? And so this is the interesting photo album or the book that this author want to remind you. So there are some page or many page. How come our universe change from this image or this small size up to nowadays so many galaxy and cluster and etc. Is it clear? This first page. Okay, so astronomers are trying to fill in the blank page like this heading in our photo album of the infant universe. Okay, and before we continue to talk about this 21 cm cosmology, we would like to look at the cosmic timeline about that, what we understand right now. So here is the, from the left to the right, this is the timeline, all right? At the beginning, okay, start of Big Bang expansion. And you can see after Big Bang 10 to the power minus 43 seconds, the space and time are this tangle and blah, blah, blah. And so you can follow this timeline, but I won't go through the details because you can easily to refer it. And you can imagine at the beginning, we have infinitely dense in density and very high temperature and small size, okay? And so you can imagine very energetic, but at that time, low atom, molecules, or even matter at the beginning. But of course, this energy will change into matter, because energy in some sense means matter. But you can see the timelines here we mentioned. And for this timeline, I would like to emphasize there is a period, okay? And after this, what we so-called WMAP discovery or even pan satellite, okay, more updated, because this article was written at 2006. You can imagine at that time, low pan satellite information. Right now, of course, we should change. And here we want to show you this purple colors. We would like to indicate this is what we so-called dark age, and which is sandwiched between the release of microwave background radiation and the formation of first star or galaxy. This is the Wolf time scale. So if you are not familiar with redshift, you can also talk to the cosmology with such signature location on the timeline about different period and history of our universe. Okay, here is another one which is continue to the time scale for the cosmic timeline. And you can see, of course, at some specific moment, what we so-called dark age should be end, and because some star formed, okay, and the universe not so dark, they produce radiation either in UV or in higher energetic way, and they try to shine or let the universe become observable, okay? So this is our brief timelines. at the last, the author used this beautiful picture, which is captured from the infrared at the beginnings from Spitzer, am I right? I forgot. Okay, use the space infrared detector. Okay, M31. So from this picture, you can see if we observe it on the infrared band, we can also see many interesting structure for this M31. But why this author use M31? I guess one of the reasons is M31 by our good condition, related with good condition of our sky and use our naked eye, we can see a poor image, okay, on the sky about M31, and so why the author select M31, okay. Otherwise, nowadays probably we will put M87 or and etc. Right? Okay, so this is a brief timeline. So I hope you can read it carefully so that you can see different phase related to the illustrated diagram that I mentioned at the beginning, so that you can know more about the history of our universe. Okay, and back to this picture, or even no, this picture. Yes, this picture. And here we call it dark age. And you also know that as we introduced two major challenge, okay, in astronomy, so-called dark matter and dark energy. Sometimes the astronomer or astrophysicist at this present moment, they may not fully understand, or even they don't know, they will call it dark. Okay, dark. So here, from this illustrated diagram, based on some theory and prediction or calculation, they will say the first star should be at this period. Okay, at this period. Why? Because we told you the observational cosmology show you the CMB they detected, and also at the last Z equal to nowadays, or even 1 or 2, we have many sky survey program, optical or other band, and we can see many galaxy cluster and etc. But in between that, how come they change? Okay, related with gravitation, and our universe can have different ingredient like what we detect and see right now, but start from this baby image. So we need to know more. Around 20 years ago, many people start to think, how come they can detect this period? Or even right now, as I mentioned before CMB, can we detect anything on it so that we can check the standard model or standard theory which satisfy to our suggestions or not? So you can see some pioneer, they all are very smart guy. They start to think about how come they can detect, or is it possible to detect any evidence related to such so-called dark age or before CMB period. So they think many possible solution already. Okay, and today we major focus on this. Okay, and this is another description from another gentleman. Okay, that they discussed before. So like here, corresponding to CMB, and the Z equal to 1100, as I mentioned before, and the corresponding suggested dark age, and of course, in some sense, once the first star or galaxy form, it should be produce emission, and so they also put the name so-called cosmic dawn, and another epoch so-called reionization. You can imagine at the beginning, start from Big Bang, we produce some fundamental particle, electron particle, and photon, and blah 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 blah. However, at that moment, before CMB, our universe was not transparent, okay? Since the small size of our universe and many photon from CMB or no, from after Big Bang, they want to come out. Unlucky that many electron or other particle will have what we so-called scattering and cannot allow them come out, and that's why we cannot detect easily until our universe keep expanding and temperature lower down. And let's say based on their calculation, they said roughly doing the CMB around Z equal to 1100, which is roughly equal to 3000 Kelvin. At that time, the photon can come out, and in some sense, that's why we can detect it. So at the beginning is ionized, okay, and then after expansion and the temperature cool down for our universe, some electron probably combine again with some positive particle, and so become neutral. However, when the first star form, they also ionize, produce radiation to some specific position, and that's why we call it reionization. And then at this moment, our universe ionize again. That's why scientists use reionization, the words. And HUD corresponding to Hubble diffuse image, okay, a bit old, but still very useful when we discuss it. And so we move on to some simple theory about this 21 cm cosmology. You see, when we use the word 21 cm, sometimes has a little bit misleading, because we call it 21 cm cosmology. Now we use our radio telescope to detect it, but we do not say we detect 21 cm radiation, because you look at this formula. At the time, the people think about use radio telescope or radio array to detect the 21 cm signal, which is related to hydrogen. And for the hydrogen that they discussed was very early universe. So at that time, should be 21 cm. However, our universe has expansion, you can imagine. All right, so if you look at the wavelength at that time, maybe 21 cm. However, while now we detect it, we should have such expansion. So times 1%. If you are talking about wavelength. Similarly, if you are talking about frequency, you should divide it by, at the moment they emit is 21 cm divided by 1%. So you can imagine what we detect nowadays due to this expansion is not 21 cm in wavelength. All right. So go back to some radiation mechanism at that time. You can imagine after Big Bang, our universe is still very energetic, but due to expansion, of course, our universe expanding and then temperature drop down, but still you can imagine like a congee soup until CMB. That's why we can detect the afterglow of Big Bang we suggest. However, what we want to say, so like the figure we mentioned here, still no more molecule or particle, okay? And then now we want to detect some signal on it. Someone suggests that, can we use 21 cm signal? Because after Big Bang, you can imagine they produce a huge amount of hydrogen. And for what we so-called neutral hydrogens, like here, they have a mechanism like this. This is so-called spin temperature. You can imagine the electron rotating around the proton for the hydrogen. And in quantum mechanics, we have, or atomic physics, we have a concept so-called spin. Okay, like here, spin up and spin down. And for this case, if the electron, which is red color, which is spin down, and here the proton is spin up, and this is called anti-aligned spin. I mean the spin, one is point upward, one is point downward. Okay, in some occasionally, this spin down arrow from electron will change to spin up. Oh, let me see whether I have another photo about that. Okay, it doesn't matter. It doesn't matter. Okay, continue. So they have what we so-called hyperfine structure they can explain. So the number of these spin up and spin down electron and proton can be described by what we so-called spin temperature. So this is a ratio, okay, for spin temperature. We will show you the formula. So in some occasion, if the electron change from spin down to spin up, you can imagine the energy level, they will change into higher energy level. So once they change it back, point to downward, originally point to downward for this red color electron, and change to upward, okay, this is called aligned spin. While now is so-called anti-aligned spin. So if they are aligned, this is in higher energy level, and after some occasion, they can spin down again, and they will emit what we so-called 21 cm wavelength emission. So this mechanism is the probability occur this spin up, spin down, flipping radiation is not very high. But you know, as I mentioned before, after Big Bang, so many hydrogen, okay, and so this can be occur. So this is one of the basic idea. How come we get the 21 cm radiation? And this is what I mentioned already. Okay, more details. What we want to say, this formula, n sub 1 over n sub log corresponding to these two proton and electron, they are spin up ratio, and more aligned spin, of course, this temperature, we can introduce a temperature to discuss this situation. So in this formula, you can imagine here related to this T sub S, spin temperature, K constant, and this is the frequency, and Planck constant, and etc. So we introduce this so-called spin temperature on it. And now, on the right-hand side from this slide, you can also see that, as we mentioned before, we can use different receiver in radio band to detect different frequency. And based on the formula we mentioned before, you can see here, if this is 1.42 gigahertz, okay, and divided by 1 plus Z. So like this one, if we are talking about Z equal to 6, you put here and you put back this F for 21 cm frequency, you can easily to get this 200 megahertz. So in our ground-based detector, if we have a telescope receiver related to 200 megahertz, which corresponding to this specific time of our universe, Z equal to 6. If you still remember, I told you at the beginning, for CMB, Z equal to roughly 1,100, sorry. And so here, if we are talking about 100 megahertz, corresponding to Z equal to 13, 70 megahertz, Z equal to 20, Please remember these few values. We will tell you more about that, why we specify this 40 megahertz. I assume the signal that you detect really from our early universe, okay, with 21 cm emission. So if you have a receiver on this band or this frequency, we are talking about which position and history you are detected. And similarly, if you are talking about the age for the universe, Z equal to 6 equal to 1 giga-year, Z equal to 10, 500 mega-year, and pop, 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 pop. Okay, this is so-called the spin temperature and 21 cm hyperfine line of neutral hydrogen. Okay, now I would like to answer you why we introduced MWA before, and because to study this 21 cm cosmology, we have several types of observation, and at least two types I would like to talk to you today. One is so-called 21 cm intensity mapping. And intensity mapping, you can imagine why we install so many detectors in Western Australia or South Africa, because we want to detect the sky on different positions at the same time, and even they have different wavelength. So means we can monitor all the different position and time scale of our universe. And that's why we use an array. However, you can imagine for the array that we take into account in this situation, the price or the cost should be very, very higher. Okay, like, wait, let me show you first. Like, lock this one. Like this one, okay, this slide. You can see so-called LOFA, MWA, and 21 CMA, and GMRT from India. This is from China, and paper from South Africa and US, and MWA from Australia and Holland for LOFA. LOFA has 10-year history already, okay, in Europe. They install in Netherlands and Germany, okay. In UK also have some, as far as I remember. Okay, they put this array to detect this so-called 21 cm signal occur from very, very early universe. Right now, the result, may I say a few words? Paper can upgrade into second phase, paper 2, and PAPER, we call it paper, doesn't mean a paper, okay, a piece of paper. It is related to precision array to pop report of reionization. And up to now, the array, they got some result, but the result still not related to the exact 21 cm signal, okay? They try to push to the limit that they want to detect. So I think if their work keep continues and they can upgrade their sensitivity, probably they may be detect some interesting signal very soon. However, this array up to now, no one detect the real signal from this 21 cm signal for our baby universe. And someone, they consider, okay, this is huge amount of money, okay, not easy for Hong Kong government. Of course, they cannot afford, even they afford, they don't put this in the first priority. You can see lower left-hand corner, this is 21 CMA project from China. They invest a huge amount of funding and money in Xinjiang. They also fail to detect, but lucky that this array, they change to another project related to higher energy physics, as far as I know, okay. And in India, GMRT at the beginning, they are not working on low frequency, but right now they all change this 45 antenna into low frequency and some middle frequency range, and they produce many interesting results and paper. Okay, and LoFa, of course, many results. However, this is quite expensive, and two gentlemen in 2018. Let me see whether I can show you these two gentlemen here. Okay, please wait. I'm sorry, my PowerPoint was happening today. Yes, this one. And two gentlemen, two important gentlemen, I will say. One is called Alan Roger from Haystack Observatory from US. Because I remember this guy very much. You know, in our Hong Kong, around 18 years ago, we bought the first small radio telescope from his company. Okay, and that's why we set up on the HKU physics building, so-called SRT, right now stop production, okay, for this company. And this company is a subsidiary small company from Haystack Observatory and MIT, and we bought it. And I remember last year when I talked about this small radio telescope, I also said Romania also joined this HOU hands-on universe project in terms of radio astronomy, and they should have a site, have the small radio telescope. Anyway, Romania also joined. So if you can apply an account, probably you can remote use it. Okay, come back here. So the second offer in 2018, these four gentlemen, and the first offer, so-called Bowen. The last slide, I call their paper. They published a paper in Nature, and on the 1st of March, the paper published. And I was a bit unhappy at the time because I also want to detect this signal. But of course, these two respectful professors did very well from my point of view, and they construct these antenna or this detector. You can see at the ground floor, they put a latch and some latch, okay, metal latch, so that they can let the antenna collect the data or the signal better, okay. Okay, anyway, this is like a ping pong table, you can imagine, roughly 2.7 meter in length, and the height 1.5 meter, and the width around 2 meters, something like that, and located in Western Australia. And these two gentlemen, they use a method so-called single antenna to study the very early universe radio signal. Then you may say, Sing, you mentioned that the big project like paper 21 CMA or GMRT, LoFa, and etc., they fail to detect. Why we use a single antenna to detect it? Okay, this is a good question, because we are talking about the signal for our universe, okay? And you can imagine this signal should be in all positions, because from our simple understanding and observational result, our universe roughly is isotropic and homogeneous. So in this sense, even we put some ground-based single antenna, we can use what we so-called average spectra idea to study the 21 cm cosmology. So I told you before, we say 21 cm observation at least two different modes. One is called 21 cm intensity mapping. So you can see the sky at different positions. We are monitoring it, okay, with different wavelength or with different bands to look at it. Okay, this is looking at big fields of view, okay, or location on the sky. But in some sense, we can also use a single antenna to measure what we so-called air phase spectrum. So what does it mean by air phase spectrum? And you can imagine, like the case in Hong Kong, okay, in February, okay, let's say in the last February, Hong Kong was cold, okay, and from day to day, the temperature was not the same. Okay, in March, we also cold. However, let's say we also detect the warm day from February and the very cold days from March. Okay, we try to average these 2 months. We still to say, assume the temperature difference for February and March not much, and then we can still use the average method to say our Hong Kong's temperature in February, okay, is colder or cooler than March in some sense. So here, because we are talking about for this single antenna, because we would like to talk about the signal from the universe in all different positions, they are doing averaging. And so even in some sense, this averaging should be the average of different position and location. So even they use a single antenna, they may can say something about that. And that's why they produce at that time in 2018, they produce a spectrum about this antenna on 70.5 megahertz result. And let me see, yeah, this is the result. And this antenna, they call it edges. I forgot the full names, so it should be related to the epoch of the ionization and dark age, something like that, and published by this gentleman. And they got this interesting result. And okay, and this interesting result, I should say, to all of you, wait a minute about this part. Okay, this formula, because I stopped and I said we use what we so-called air phase spectra. And why? Before we talk about that, we would like to show you here corresponding to the CMB result. And you see the CMB result difficult to tell you the evolving from CMB and change to galaxy, okay? So that's why 20 years ago, and many gentlemen try to propose this 21 cm detection, whether they can try to open the secret for the dark age and etc. And here, corresponding to what we so-called bright test temperature, you can imagine our detector here corresponding to Z0, and for this frequency, and they pass through this hydrogen cow, let's say, or at different times, Z equal to 13, Z equal to 0. This is present day. And now this is 13, as I mentioned before, many years ago for our universe. And they propose the air phase temperatures for this sky spirals can be represented by this model. And this model, of course, they use the detailed and well-established theory, atomic physics, and some astrophysics, and etc. Like here, they also introduce Wolfson's field effect, but I don't go through the details because this is related to the atomic physics, okay? So here, but I introduced the spin temperature to you before. Spin temperature, and this T sub gamma corresponding to the CMB radiation. So I have a page here. Okay, everyone. And because we want to detect this dark, and they have a collaborative work. I don't know how to pronounce, means here they have such, how to say, how they cooperate. So what I want to say, despite lack of star at the dark age, you can imagine, okay? And aware process can cause hydrogen gas to go dimly, because the universe after Big Bang, you see major corresponding to hydrogen, okay? And we show you the dark age, which is dark, and how come we can detect any signal about that? The gentleman proposed aware process can also cause the hydrogen gas to go dimly, and maybe this is related to, let's say, for hydrogen to glow, we have this particle corresponding to the photon from CMB, and the hydrogen itself corresponding to some atom, okay? They have what we so-called own kinetic energy. I remember I introduced in lecture 2 this kinetic energy, okay? Anyway, the matter, okay, higher than the absolute zero temperature, they will have such so-called kinetic energy, although very cold at that time, you can imagine. So here we want to show you for hydrogen to go, there had to be a source of energy. And this energy source can only be so-called kinetic energy by the atom and released by the collision between atoms and the photons of the cosmic microwave background radiation. All right, the first half for this slide, want to remind you at that baby universe, okay, we need to provide an energy source so that maybe we can glow up a little bit for the hydrogen, and this little go up and maybe can be detected in radio band. However, these two sources, just like in the second part of this slide, lighter source was strong enough to cause hydrogen to go by an unusual means, by usual means, sorry, in which the electron gets bumped into higher orbit. Okay, like here, they go to the higher orbit, and then from higher orbit, this electron will go back down to the lower orbits, and they produce the radiation. And this is what we say the spin up, spin down, okay, and possibility. Okay, and now, another picture. Sorry, why I lost it. Okay, and here. Okay, now here. I'm sorry, I have another slide which is magnify this part. So in this case, this relationship, look at the bottom, just like a triangular relationship, and spin energy and background radiation energy, kinetic energy. Okay, and you can see that the relation between this background radiation energy, the CMB photon, okay, and the spin energy, this is based on the absorption and emission of 21 cm photons. Okay, the relation between background radiation and kinetic energy corresponding by the residue electron, and the last one, the kinetic energy and the spin energy atom-atom collision. So here is a figure, and I magnify it no more. Okay, you can imagine this is the timeline. Okay, we cut into 4 phases, and this diagram and every simple diagram I sent you already through the checkbox. Okay, you can refer it. Okay, this is phase A, phase B, phase C, phase D. You can imagine here these 3 different colors corresponding to these 3 lines, and the background radiation, atomic spin, atomic motion. So the red color corresponding to the kinetic energy, and yellow line represent the spin energy, and the green corresponding to the background energy. And here we have the description during the different age for the universe. You can say phase A, phase B, phase C, phase D, phase A at the beginning, these 3 temperature, or you can imagine integrate together, or nearly the same. all right, nearly the same. And then, I mean, at the start of the dark age, all these three temperatures were the same. Okay, phase A. And then phase B for different time side. After for a while, the spin temperature, the kinetic energy and the spin temperature began separate to this result, okay, from model, okay, and then after for a while, the temperature will return for the atomic spin, the yellow line will return to the same as the green line. So here we want to show you the relationship related to these three different type energy at the very early universe, and how come they produce this corresponding signal. And you see background radiation. Okay, go back to this formula. You can see this term. If the spin temperature minus the background temperature, radius CMB over this TS, okay, TS greater than T gamma, of course, they will have emission. Similarly, reverse, they will have the absorption. So after you plot this so-called global signal, okay, global signal for our 21 cm, you should have this, these line, these 21 cm line at different age of our universe. Okay, can I show you more? Like this graph, and A, B, C, D, E, and D is important from my point of view, because when you assume you want to collect the data, you want to check this result, they have some minimum and maximum. Sometimes it's very important that if you have data, you can check it on this diagram. You can see the y-axis corresponding to the temperature, and the temperature, may I remind you, is very, very extremely small. So here we say millikelvin, okay? I mean, based on the previous formula. And for the x-axis corresponding to the different frequency. And here, this picture I taking out from an old suggested project from America. Very, very unlucky that they finally failed to get the funding. This is called DARE, Dark Age Radio Explorer, because they want to send some antenna at the far side of the moon to study this project, And okay, on the top, you can see Dark Age, first star, first black hole. So these are the corresponding history and simulation. And this is simulation, okay? And with such theory, they related to this simulation. And let me see, here is more better simulation, but I will say a bit old, but this is some pioneer work. That's why I still call for it. And you can see at the top corresponding to some simulation result. At the beginning, I studied this topic. I was very scared because we need to do a simulation for our universe. Can you imagine? Sometimes in some sense, this is a bit crazy. However, with some help from Professor Huckle and some students and people, I found that no, in some sense, this is not extremely difficult, because you can imagine our universe, okay, at the beginning, very pure, only energy, agree or not? And after expansion for our universe, in some sense, they have atom or particle and etc. So the simulation, in some sense, may be simpler than to simulate the what we so-called stellar evolution. All right. And also some pioneer, they contribute some simple program, which is free of charge. And you can also try to install it in a Linux system or Mac system, such as so-called 21 cm fast program. 21 cm fast program. Fast means this is a semi-numerical simulation that you can simulate even you have a local computer, okay? no need to use a supercomputer or a mini computer, something like that. And FAST means 21 cm fast. FAST means they use semi-numerical code. Which means they have many simplified assumption and so that less stimulation times you need. Otherwise, we must use a supercomputer or HPC computer to do the simulation. So like 21 cm fast, and also there is another program so-called CMB fast. So fast means you can use it and simulate in your own computer with a good CPU. So based on the global signal, the FA spectrum that discussed, you can see the minimum is roughly in 70 megas. Okay, so that's why I mentioned before in 2018. Bowen and Roger, they published the Nature paper, and this paper was in very low profile. Okay, if someone not read it carefully for the Nature paper, won't care about that. But from my point of view, this is very important paper. Although they may not detect it correctly or anything. Okay. We would like to tell you some people they work on it and try on it, or even they detect or may not detect, but they start already. So in 2018, the paper was important. And I also have some times to meet some people from West Australia, so-called Professor Stephen Dengay, one of the directors in West Australia in radio astronomy. I asked him what was his comment about the detection published on 2018 paper. He said 50-50, okay, still controversial. And that gentleman was respond MWA. Okay, come back here. This is the simulation for the 21 cm global signal with respect to our universe. You can imagine from this picture, at the beginning, the color corresponding to the temperature scale. And also, you can see at different age, our universe was pure energy and something, and cosmology study it based on what we so-called density perturbation. So in some sense, the difference density, and due to gravitation, the higher density position will accumulate more and more energy or matter, and that's why they can form the star or even the galaxy and etc. Okay, so the simulation related to this 21 cm global signal based on this density perturbation. Okay, now we move on. This is the project that the American gentleman want to apply the funding and to detect it. I hope the first generation they fail. Maybe they consider the second generation program. And here I introduced some semi-numerical simulation that teach me by Professor Hackel and another gentleman. Okay, and as I mentioned before, you can install the 21 cm program, and then once you install in your computer, and then you can see whether you can change their standard model. Okay, because originally the 21 cm fast program related with the standard lambda CDM model, and these two gentlemen, Professor Hackel and the Dr. Dania, right? And anyway, they modify some code, and finally we also got some simulation with different Earth offset for the lambda CDM, or even we changed the Hubble function and we got some result, some related to star formation, some related to the density, and etc. Okay, and now, wait. Here I have an English version. I apologize. Okay, I send it to you. The Scientific America, they also have different timeline and briefly discuss the theory. How come the universe due to this different density perturbation and form like this bubble, and then this bubble, when they have the first star, of course, they will produce radiation, and anyway, they will finally form many bubbles in our universe, okay? And the 21 cm intensity mapping means want to look at different position for this bubble, see whether they match with the observation or the simulation. Okay, may I remind you, observation not yet detected, okay? Okay, this is another artist impression about that. Nowadays, more details. So you can imagine the general picture that our universe change from here to here should have a process. So this 21 cm cosmology want to study it. From my point of view, I hope they can detect, no matter which observatory, if they can detect more signal and possible signal, that's good for our human study, okay? Okay, apart from the Bowen, okay, the updated news is the following, okay? And the Indian groups, they also very good on radio astronomy. And so they create some interesting antenna, and they also install on some very low radio interference area, and such as so-called big horns for detect the global signal. Okay, detect the global signal to see whether they can collect the signal, same as the edges. And also the another Mexican, they also install it. Right now they change. They didn't use this SCI hydrogen, neutral hydrogen. HI means neutral hydrogen, and they call it PRISM. PRIZM. Yes, PRIZM. Okay, and they see their working frequency from 40 to 130 megahertz, and this is good and very interesting. Our team also want to set up one in Hong Kong. Of course, maybe nothing we can detect, but without starting, without progress, from my point of view. Okay, this is edges, and they detect this one. However, yes, the story not yet end. From this paper, they detect this result, and here you see the redshift in between 16 and 19, roughly around 70 megahertz, same as the first few slides I mentioned before, the minimum for the global signal. Remember here roughly 70 megahertz. So their detector also edges focus on this channel, and here wait. Okay. So come back here, the result that they detect corresponding to this 70 megahertz. But this absorption spectrum, the depth, which is larger than what the theory expect. So at the same time, I remember an Israel scientists, they proposed a very interesting idea in terms of dark matter to explain this result, okay? So if you are interested, please look at the volume that I will introduce, okay, 2018 on Nature paper and related to this. Okay, more recently, the Indian gentleman, they published another paper 2 months ago, I remember, yeah. they said no matter they put on a desert or a very quiet zone, radio quiet zone, they fail to detect any signal similar like this. So they publish a paper, you see, they still have a positive discussion. I won't say an argument, okay? They produce a positive discussion. So they said, the Indian gentleman, no, we didn't collect this signal, okay, this FH signal. So they have a good discussion between two teams as far as I know. So this is also the second generation antenna that they use from the Indian gentleman and they publish, but still have one more updated paper, okay, as I mentioned. So, and this is why I always talk to my team, see whether we can also put one to start up, because this is a single antenna only, log and array, okay. And another antenna like this one, but you see they always put in some area which is very less people live there, is much better. Otherwise, will affect their result. Okay, affect their result. So I no matter which team they do, I'm very happy and appreciate their work, because they start to work to see whether this possibility work based on the 21 cm detection for the early universe about dark age. So I wait for their possibility and publish more result. Okay, in this case, even our team and what we can do, we can also think about whether we can construct and the similar antenna as soon as possible. Okay. I think I update up to this moment, and then see any question and welcome any question. Yes. Anyone, if you have question, okay, you can voice out or type on the chat box right now. Let me see. Okay, okay, someone say something. Let me see. We'll be out for 2 minutes, okay. Okay, no problem. Okay, I will say this project, once the SKA they construct, probably can move on more, okay, because their sensitivity is quite high. This paper, okay. You mean can you more specific which paper? Yeah. The Nature paper or this Scientific America paper? Maybe no problem. I can okay. No problem. I will send to Dr. Braga, and I mean the organizer, and the organizer will distribute to all of you. Yeah. So no worry. Even the PowerPoint, okay, I will change to PDF and send to the organizer, and the organizer will send to all of you very soon. Yeah. If you like radio astronomy, I think, yes, this is a good topic, corresponding to radio astronomy. Or think about, in Hong Kong is very small, but Romania or even some Singapore student, any position you can think in your own country, city, or hometown, possible to install some teaching antenna. Okay, and you see the antenna I show you, they have a big team and they have a very specific and many experts on it. So their sensitivity also very higher and very good. So in this case, a lot easy produced by our amateur people, okay? But if you never try, I will say never have any result. Okay, and then let me see, Dr. Baraka or Gabriana, do yeah, one more new message. Yeah. No, I may not be the best one, okay? If we can invite Professor Stephen Hawking or any gentleman who really work on this project, in our Hong Kong PolyU, very difficult to work on it. Yeah, but we will try, no matter how difficult it has. Okay, someone asked me, most of the antenna are installed in the desert or suburban area to avoid possible artificial interference. Is this reasonable? A good question, very good question. And you asked me, very reasonable, okay? Because in those desert or suburban area, relatively the radio frequency interference is less. And of course, you know, both teams or all the teams, they did what we so-called the background noise measurement already. And like the case in MWA in Western Australia, they when they search the location, okay, they search many times already. Even like similar to China, you know, their fast telescope. I remember the gentleman select the present location. They select at least over 200 candidate, I mean the position, and also ask the expert in geology. For our case, if we install in the desert and suburban area, this is reasonable. This is reasonable, okay? But I'm greedy, as I mentioned before. You know, our Hong Kong developed radio astronomy because the weather was all the time cloudy and not easy to have optical astronomy. And secondly, some daytime observation we can use. So I'm greedy even in our city environment. We construct some radio telescope, although we know we have radio frequency interference, but we still install on it because we also try to search any good position, still have a radio quiet zone. And luckily, like our daytime observatory, okay, relatively the RFI, radio frequency interference, not very serious. That's why we can still use some of the data that we capture there. So if we don't try, we say, okay, impossible or not good, and then we won't have any result. So please do not scare. If you never try, our result will be zero. Okay, if we try, even still zero, but we earn the experience. Of course, the successor, the young people, and any other talent, they will know how to do more about that. Thank you for your question. Okay, Dr. Bracker, I'm sorry for my over one, and I will send the PDF and the corresponding paper to the register and send you the email, and please help me to distribute to all of them later. And also today's video, we will upload it soon in somewhere so that you can do revision. Bear in mind, like last week, Dr. Hodgson's presentation, I upload it very quickly, just one day or the same day. So I know many people want to learn how to do the data processing based on his full flow introduction. So please watch the video. Yeah.
Thank you. I will, of course, distribute the materials you sent me.
Thank you so much.
And thank you personally for agreeing to do this lecture, this series of lectures. Thank also to the audience who hung with us until this very last moment.
Mhm. Okay.
And if
Yeah,
there
yeah.
are no more questions, I guess we may close the meeting for today.
Okay. Okay.
Thank you
Okay.
all
Good.
again.
Goodbye. Good luck and good health, everyone. Bye bye.
Thank you. Okay, goodbye.
Bye.